Okay, we're continuing with test 1. Here we're going to integrate arc sine x dx. And remember that is using integration by parts. We had a little acronym that we used, LIATE, that you might want to remember. Logs, inverse trig functions, algebraic functions like powers of x, trig, and exponential. So this is an inverse trig, and it is a good candidate for u. So we let u be arc sine x, and therefore du is 1 over the square root of 1 minus x squared dx. And dv, if we let u be arc sine x, dv has to be everything else. So dv is dx. And therefore v is the integral of dx, which is x. You might have to look up integration by parts in the video again. So we have the integral of u dv is equal to uv x arc sine x minus the integral of v du. So multiplying x to 1 over the square root of 1 minus x squared, I'm going to write it, well, I'll go ahead and write it that way, x over the square root of 1 minus x squared dx. So now our challenge is to integrate this. But that turns out to be an easy one. And let's see, I'm going to do that right here. The integral of, well, that's 1 minus x squared to the minus 1/2 times x dx. So this is going to be a u to the n du, because we can see that if, well, I probably should call it something other than u, if w is 1 minus x squared, then dw is minus 2x dx. So all I need is a minus 2 here, and making up on the outside a minus 1/2. And now I've turned this integral into u to the n, u to the minus 1/2 du. So to integrate u to the minus 1/2, well, that's very simple. I'll go back to white now because we can just write our answer. The answer to this question is x arc sine x, and then we have minus 1/2 u to the plus 1/2, that will be 1 minus x squared to the 1/2 times 2, its reciprocal, add a constant. So that is the answer to this question. Keep in mind that integration by parts is used a lot of the time when you have powers of x times a transcendental function. And by transcendental I mean the functions that have letters in them, like log and sine and cosine and arcsine and arctangent and e to the x. So if you have powers of x times a transcendental, then you often use integration by parts. Or if you just have a transcendental by itself, like we did here, just arc sine x. Okay, the next problem is one that you would just simply square out. You know, if you square this, that you're just going to use the power rule. So we have 1 over the square root of t squared is 1 over t. Well, that'll be a natural log. Minus the product of the two is minus 1 over the square root of t. Double it, so it's minus 2 over the square root of t, and plus 1 dt. So we have then the integral of 1 over t minus 2t to the minus 1/2 plus 1 dt. There's no reason to split those apart because we can just integrate term by term. The integral of 1 over t dt is the natural log of the absolute value of t minus, well, we're going to have 2 to the plus 1/2, t to the plus 1/2, raising it by 1, multiplying by 2, I'll have minus 4t to the 1/2, and the integral of 1 dt is t, and add a constant. The integral of 1 over the square root of the quantity 1 minus 4x squared dx. Well, this one, let's try it the wrong way once, so you see that there's nothing wrong with trying it wrong, and you'll see that it doesn't work. If you were to let u be 1 minus 4x squared, hoping that this might be u to the minus 1/2 du, you'll see that your differential du is minus 8x dx. Well, we can get the minus 8, but we can't supply a factor of x. So this doesn't work. Well, you've only got 9 little integration forms that you know. This certainly isn't e to the x or sine x or cosine x. The one that it might be is this one. So you bring to mind this integration form, the integral of 1 over the square root of 1 minus u squared du, and that was arc sine u. So maybe our problem will fit that. So let's try. In that case, this is 1 minus 2x, the quantity squared. So u would be 2x, and du would just be 2 dx. And we can arrange for that. We can multiply by a 2. So let's rewrite this problem so you can see it. We're going to have to supply a 2. I'll put the 2 dx on top here, over the square root of 1 minus 2x, the quantity squared, and I have to multiply by a 1/2 to make up for the 2. So I have 1 over the square root of 1 minus u squared du. So this is then 1/2 arc sine 2x plus a constant. In this problem, we see a rational function as the integrand. A rational function is the quotient of 2 polynomials, and in that case, we first check to make sure it's proper. The degree of the top is 1, the degree of the bottom is 2, so it is proper. The degree of the top is less than the degree of the bottom. So we try to factor the bottom, and we see that this is x plus 1 over 2x plus 1 times x minus 1, factoring. So we will set up partial fractions. These are both linear factors, so we will have a over 2x plus 1 plus b over x minus 1. And we have to solve for a and b, so I go across and I clear the fractions, multiplying both sides by that denominator. Well, it cancels on the left, and I have x plus 1 equals, and when I multiply it over here, I get a times x minus 1 plus b times 2x plus 1. And if you don't remember how to set up these partial fractions and do the algebra, then look back to the video on this, and you can remember. You'll definitely have a partial fraction like this, or I'll do one more example where you have an irreducible quadratic factor. Okay, so here, well, I'm going to let a be equal to, x be equal to 1. If x were 1, this statement is true, so 2 would be equal to a times 0 plus b times 3. So this would give us b is equal to 2/3. And let's see, another handy value would be x equals minus 1/2. If x is minus 1/2, then when we plug it in, the b term will go away and we can solve for a. So minus 1/2 plus 1 is 1/2 is equal to a times minus 1/2 minus 1 is minus 3/2 plus 0. So now we can just solve directly for a. A is equal to 1/2 times minus 2/3 or minus 1/3. So then we'll rewrite the integral. Our integral is now the integral of a over 2x plus 1. So I'll bring the minus 1/3 out and write 1 over 2x plus 1 dx plus b 2/3, might as well bring it out, times 1 over x minus 1 dx. Now these both will fit the pattern 1 over u du. This is what we'll be using. The integral of 1 over u du is equal to the natural log of the absolute value of u. So in this case, our u is 2x plus 1, so we need 2 dx. So I will multiply by 2 here and 1/2 on the outside. Here our u is x minus 1 and our du is dx, so we don't need an adjustment. And now we can just integrate using that, what I wrote up in the corner, minus 1/6 times the natural log of the absolute value of 2x plus 1 plus 2/3 times the natural log of the absolute value of x minus 1 plus a constant. A word about rational functions. Look at these three integrands. Each one of them is a rational function, but none of them require partial fractions. And the reason is because the denominator in each of these is already an irreducible polynomial, an irreducible linear or quadratic. The first one is just linear, so if you were going to integrate this, I would call u 2x minus 1, and in fact, you know what, we should do these. These are perfect examples. They are rational functions. They do not need partial fractions. 2x squared plus 1 cannot be factored, and x squared plus 1. Let's just do 2 of these just for the, I'm going to do this one here, and I'm going to do this one. Okay, so the first one, let's do it real quick. I don't like the 2x minus 1 in the denominator. It's not a natural log because it's not 1 over 2x minus 1, and I can't split using the denominator, so I'm going to name it away. I'm going to let u be 2x minus 1. Du then is 2 dx, and I want to solve for each of the parts and put this in terms of u. So I need to solve for x because I see it here. So x would be 1/2 times u plus 1, solving for x, and I'm going to need dx, so I might as well just write dx is equal to 1/2 du. Now I use those to write this integral in terms of u. 1/2 times u plus 1 is x over 2x minus 1 is u, and dx is 1/2 du. Now, of course, I'll pull both factors of 1/2 out, and I have 1/4 times the integral of u plus 1 over u, which is, now I split using the numerator. U plus 1 over u is 1 plus 1 over u. du, which is, well, we can integrate. 1/4, the integral of 1 du is u plus the natural log of the absolute value of u. Now putting our x's back in, we have 1/4 u, which is 1/4 times 2x minus 1 plus 1/4 the natural log of the absolute value of 2x minus 1 plus a constant. So in that case, we didn't really, it's substitution, but it's a substitution where you need to make the substitution and change the entire integrand into a u integrand. And what happened there was that the denominator, which we couldn't use to break the fraction into two, we named it away. We made it one term. We called it u. Then the numerator became a sum, and we could split. Now the other one I was going to do was the integral of x minus 1 over x squared plus 1 dx. Well, this one, I know what 1 over x squared plus 1 would be, and x over x squared plus 1 would be a simple substitution. So I'm going to split. But I'm not using the denominator, I'm using the numerator. X over x squared plus 1 dx minus the integral of 1 over x squared plus 1 dx. Well, on top here I have x, so that gives me a du for u equals x squared plus 1. Du is 2x dx multiplied by 1/2 on the outside, and this one is just arctangent. So it was a very simple integral, and we get 1/2. Now this is, remember, du over u, so it's the natural log of x squared plus 1. I don't need absolute value there, minus arc tan x plus a constant. Those are two good examples to study. They're not complicated, but you have to be able to see when you need partial fractions or when you don't. If the denominator is already irreducible, in other words it's linear or it's a quadratic that you can't factor, then you're not going to use partial fractions. Evaluate this limit by recognizing and calculating the definite integral that it represents. So this is a Riemann sum, and it's taking the limit of a Riemann sum as n goes to infinity, so it's a definite integral. So let's see, our function, these are pretty easy. You can see that the function f of x will be, well, it's the cube root of x, and a is equal to 1, because we know that this is a plus k jumps of delta x. F of a jumps of k, a plus k delta x. So a is equal to 1, and delta x, you can see, is 7 over n, and so b must be 8. And this is the integral from a to b, 1 to 8, of the cube root of x dx. We wanted to evaluate the limit, so we need to integrate this. That's x to the 1/3, so using the power rule we have 3/4 x to the 4/3 evaluated between 8 and 1. 3/4 then times the cube root of 8 is 2, 2 to the 4th 16, minus 1 to any power is 1, so we have 45 over 4. We evaluated a limit by recognizing that it was the limit of a Riemann sum and therefore had to be a definite integral. So we found the definite integral and evaluated that. So here we want to find the area of the region, and it's bounded by the line minus 3 minus x and the parabola x equals 9 minus y squared. Now remember, to find area we drew a representative rectangle, and the rectangle would be vertical or horizontal. Notice if we drew it vertical here, if the top would be on the parabola, the bottom would be on the line. But as I went by over to this area, the top would be on the parabola and so would the bottom. So we wouldn't get a representative rectangle that would work all the way across. So instead, I choose, in this example, I want to choose my rectangles horizontal, because no matter where I draw the rectangle, here, here, or down here, the left tip is on the line and the right tip is on the parabola. Now we called dA, the differential of area, the tiny piece of area, to be equal to the area of that little representative rectangle, which is its length times its width. Well, its length is the right-hand x minus the left-hand x because it's horizontal, and its width is a little tiny sliver of the y-axis. It's dy. So what is x on the right? Well, let's look at our x on the right is x equals 9 minus y squared. So that is 9 minus y squared. And x on the left here is x on the line. So we have to solve here for x on the line. Here, if we solve for x, we'd get minus 3 minus y. So it is x on the right minus x on the left minus 3 minus y, and all of that multiplied to dy. So our area then will be the integral of dA, and let's simplify this. Let's see, it's 9 minus a minus 3, so that's 12 plus y minus y squared dy, and we need to find our limits of integration. To find the limits of integration, I need to know this intersection point and this intersection point. It looks like it's going to be from minus 3 to 4, but we should check. Well, I have x solved for there, so why don't we say 9 minus y squared is equal to minus 3 minus y at the two intersection points. So let's see, we have minus 3. I'll bring everything to the left. So I have 12 minus y squared plus y is equal to 0. Or, excuse me, I've got to go over here. Well, maybe I can scroll down a little bit. So if we take the quadratic, I'm going to multiply by minus 1. Y squared minus y minus 12 is equal to 0. We get y minus 4 times y plus 3 is equal to 0. And we do have y equals 4 up here and y equals minus 3 here. So that's just checking, and we have minus 3 on the bottom and 4 on the top, and this would be the integral that represents the area of that region. So here we have a volume problem. So calculate the volume, or just set up the integral that represents the volume of the solid generated by rotating the region about the x-axis. Okay, so we're going to rotate around the x-axis. Where's my pen here? Oh, here. Okay, so I draw a little arrow telling myself the axis of rotation, and then I go down, and best I can, I draw a mirror image of the region that I'm rotating. And now I just give it a little bit of 3. It's hard to do and hard enough with pencil, but even worse on using this tablet. Okay, so imagine taking the blue region and spinning it around the x-axis, and every point in the region generates infinitely many points in space. So you have a thing on the outside looking at it like we are, it would just look like a cylinder, but on the inside it would be scooped out and it would have a hole on both ends. Okay, so let's see. We want to find the volume of this. So I would draw one cross section. Oh gosh, this is terrible. Okay, so I'm drawing one cross section, and we know that the area of that cross section, the area of the cross section would be A of x is equal to, well, it's a washer face with a hole cut in it, so it's big R squared minus little r squared times pi. Pi times big R squared minus little r squared. The big circle minus the area of the little circle. Well, the big radius is from the x-axis up to here, and that is 3. So the big radius is 3, and the little radius is, well, it's from the x-axis up to the curve here. So that is y. The y on the curve is e to the x. So we have then the area of the washer face is pi times 9 minus e to the x squared is e to the 2x. So then our volume will be the integral of a of x dx. So I'll put the pi here, and my integrand is 9 minus e to the 2x dx, and I need to integrate from, well, from 0 to 1. So my limits of integration are from 0 to 1. You know, I just made a mistake there. I looked down. Now I see why so many of you made this mistake on the test. I looked here and I saw 1. So I thought, oh, 0 to 1. I wasn't looking up here. It's not 1. We need to know the x-coordinate of that point. And just as I was going to go on to the new slide, I looked up here and I thought, hey, that's not x equals 1, because y equals e to the 1 is e, not 3. So in order to find the x-coordinate of that point, I have to solve e to the x is equal to 3. So x is equal to the natural log of 3. This upper limit is natural log 3, not 1. I shouldn't have put the 1 on the graph there, because I can see why some of you just quickly looked there and thought it was 0 to 1. Look at your region and make sure that you carefully know what the intersection points are, because those will be the limits of integration. And in this last problem, we're going to take the same region, but this time we're going to spin it around the y-axis. So best I can, I draw the mirror image on the other side. I usually try to make it look three-dimensional so I can imagine it, and it looks like a solid bowl. This time we can see that our cross sections will be taken perpendicular always to the axis of rotation, cross sections perpendicular to the axis of rotation, and so every one of my cross sections will just be circular, and the area of the cross section, a of y, it's a function of y, a of y will be pi r squared, where the radius is equal to this distance right here, the x-coordinate from 0 to the x-coordinate here. Well, if y is e to the x, then we know that x is equal to the natural log of y, solving for x. So our radius is the natural log of y. x on the right minus 0x on the left. Horizontal distance. So a of y is equal to pi times the natural log of y squared. And our volume, I might as well just stay right here in the white, the volume will be pi times the integral of the natural log of y squared dy, and our limits of integration, I think this time we can see they're from 1 to 3. From 1 to 3, and that would be your answer.